Good morning, everybody. Well, we're very pleased today to have Gavin Esler from UCL as a sort of guest speaker. And Gavin has done lots of nice work on turbulence, nonlinear waves, vortex interactions, often inspired by GFD. And today he's going to tell us about beta plane turbulence. Thank you, Gavin.
Thank you very much, David, and thanks for inviting me. So as you say, this is some work that I did with a former PhD student, William Jackman, which William unfortunately not in science anymore. I'm trying to make it. Yeah, there's a laser pointer, but that's not very bright. So William sadly is not in science anymore, but he did most of the work. So anything good in this talk mainly is down to him. So why should we be interested in beta plane turbulence? Because I'm going to be talking mostly about a model equation. So we've got to give some motivation as to why anyone should care about it. So one obvious thing is that this model equation has been kind of widely considered to be a kind of a fundamental model for the formation of jets on the giant planets, and also a variation of it is which is often called the Charney-Hasegawa-Mima equation, is kind of important for layering and tokamak fusion problems. So this is the equation we're going to be talking about with a view to understanding this problem of jet. The key point is that this model equation forms jets which resemble those on giant planets, and it's a fundamental kind of canonical model, and the aim is to understand it as much as possible. So what's in this equation? Well, it's an advection equation, if you like, for a quantity called the absolute vorticity, where zeta here is the relative vorticity, which is just the Laplacian of the stream function in this problem, and the absolute vorticity which is conserved is just zeta plus beta y. So beta y is the planetary vorticity gradient, which represents the fact that the rotation rate on a planet varies with latitude. And the equation is forced primarily by a stochastic forcing term, which has a scale square root epsilon, where epsilon can be interpreted as the energy injection rate, so long as this is suitably normalized. And the idea is that this quantity eta is a white in time noise with some spatial correlation function given by pi. What else do we have? Then the system is damped by a frictional drag, and this is a turbulent model, so it's going to create two-dimensional turbulence, and there's going to be a cascade of entropy to small scales, and we need something to remove that entropy if we're going to understand this model numerically, and that's done by a hyperdiffusion in our formulation. So this is a very standard model. It's been explored by a lot of people. Let's first talk a little bit about how one understands the effect of the parameters in the model. So there's lots of ways of non-dimensionalizing it, but when you read the literature and think about what's going on, if you like, the most important kind of non-dimensional parameters to think about, or at least in our opinion, are these three, and they can all be interpreted as ratios of length scales. One key length scale is called the Rhine scale, and it's sort of a typical root mean square velocity, which can be formulated in terms of the energy injection and the friction like that, divided by the beta parameter square rooted, and that turns out to be the length scale in this problem on which jets form. There's also what's called a transition scale, which is just by these authors. If you like, it's the scale at which the energy which you're putting into the system enters into Rossby waves. If you're injecting energy at scales larger than this L epsilon, and it goes into just turbulent fluctuations at scales below this scale. And then there's the domain scale, and we're going to be working on doubly periodic domain. And there's also a forcing scale, which is like, if you like, it's the decay scale of this correlation function of our wide in time forcing. And you can find a regime which the outcome resembles jets in the giant planets in a particular limit for these parameters. So Q, if you like, is like a quantization number up to an arbitrary multiplicative constant. And the idea being is the number of jets will scale linearly with Q. So if you have Q large, you can have lots of jets. There's an astrophy parameter kind of controls how jet-like the flow is, and as you increase Z, the equilibrated state in this model turns out to be more and more zonal. In other words, you get jets which are more and more parallel as Z increases. And then the other parameter that's we're going to consider is this ratio of the forcing scale to the jet scale, which we're calling F here. And we're going to be interested in the regime where F is much less than 1. And the idea is that in the giant planets, the source of energy, whether it be through convection or baroclinic instability or whatever mechanism you suppose is dominant, is all occurring at a scale which is much smaller than the jet scale, which is given by the Ryan scale. This is kind of formulating the limit that we're interested in. And so what happens when you run this numerical model? Well, you see you end up with an equilibrated state, typically that looks something like this. You have asymmetric jets, and the asymmetry is introduced by the beta parameter. So, in particular, the eastward jets are kind of sharper than the westward jets. And we'll maybe come back to a little bit about why that is later in the talk. You also see something which is often called potential phenomenon called potential vorticity homogenization. So this quantity is plotted as the absolute vorticity zeta plus beta y, and you often see layering in this quantity in the equilibrated state. And there are lots of waves, and there's the effect of the forcing you can see on the smallest scale in this problem. It is a very typical outcome, which a lot of people have demonstrated in a lot of calculations over the years. These are the actual values of F, Q, and Z for this parameter. So Z is reasonably large at 5, and the flow as a result, and the flow is most of the energy is in this zonal flow in the equilibrated state with some small residual in the eddy field. The scale separation between the forcing and the jets is not very large in this problem, but we'll look at some problems with smaller F later. What do we want to know if we want to understand this problem theoretically? Well, what would be really nice would be to kind of have a closure in the momentum equation. So supposing you take some ensemble or zonal average represented by these angle brackets. It doesn't affect the outcome very much, depending on what averaging process you use. And you look at the zonal or the equation for the zonal or the east-west winds. Well, you've got an equation which involves only one unknown, which is this momentum flux convergence term, or the Reynolds stress. And the idea of a closure is, well, is there some way in which we could express this momentum flux as a functional of the flow on the model parameters? And why we want to do that? Well, that would be kind of some fundamental theoretical understanding in this problem. And in an ideal world, we could have a local closure where f is some function of u and its derivatives. That would be really nice and would close the system and make a nice parameterization for these types of flows. So that's kind of the goal. And a lot of people have kind of worked on this problem. I'm only going to mention two of them to start with. And these are two papers that I want to kind of discuss a little bit as the talk goes on, because one interesting thing about them is they seem to have a result which is in direct contradiction with each other, although both of them turn out to be correct, but it's a little bit subtle as to how they can both be correct. And the first one is this result, which I think was first mathematical proof of that is a kind of correct result for a wide class of systems by Voyer and Boucher, is that in the limit of small friction in this limit that we're interested in, where the forcing is much smaller than the jet scales, there's a wide class of regimes where the form that you put in for the stochastic forcing doesn't matter, and the momentum flux turns out to be equal to the energy injection divided by the shear rate of the flow. And we'll come to a bit about why that is. You can actually then solve the equation for the momentum flux under this closure, and you get an equation for the jets with an arbitrary constant that you can fit to jet profiles. And this seems to do a reasonable job for, or can be made to do a reasonable job for the flow profiles in between the jet minima and maxima, because you have obviously have a serious problem with this closure, which is not going to work when at the jet cusps where the derivative of u is 0. So this is a kind of useful formula for some situations, but obviously doesn't apply to the entire flow. So another slightly older paper by Srinivasan and Young, also, which is kind of going to be maybe the main focus. A lot of what I'm going to talk about is reviewing this result. Oh dear, what's happened? Hang on, what's happened? Yeah, okay. Yeah, good. Right. Sorry, I'm not going to be put off. So one curious thing is that they prove is that if you have isotropic stochastic forcing, they actually prove a result in their paper that the momentum flux is always 0 for that case. That almost seems to be in contradiction with this. The weasel word "almost" here is the get-out clause, and so we're going to explain how both these things can be true over the next few slides. The reason why we're going to be looking at the Srinivasan and Young in particular is that they actually give a formula for the momentum flux which is valid for all friction, whereas this result up here is valid only in the case of weak friction, which corresponds to highs and ostrophy in our problem. So what interested William and I in this problem, made it a good topic for his PhD, is that this is a puzzle, or at least a puzzle to us. It turned out that there are a lot of hints in the literature as to, that will help us to resolve it. Could these results both be correct? And whenever we started the problem, we had no clue how they could both be correct. One thing that's kind of was worrisome about the Srinivasan and Young result is that whenever you do a numerical simulation with a sort of quasi-isotropic forcing, there's always a sort of discretization issue if you're working doubly periodic domain. These always result in non-zero momentum fluxes, so that seemed to contradict the Srinivasan-Young idea. And we wanted to understand properly what happens at the jet cusps where the shear is 0, because obviously this Fourier-Boucher result, which was kind of suggested heuristically in a lot of earlier works, obviously fails there. And then the obvious thing that kind of proves that this can't be the whole story is that the jets in this beta plane jet problem, they emerge on the Rhine scale, and the Rhine scale involves beta. So there's no way in which a closure which depends only on the shear can possibly be the whole story. Something else is going to has to happen to make jets appear on the Rhine scale. And so there's a question: how does the beta effect enter the problem? So we're kind of resolving these puzzles was kind of the topic of William's PhD. So I mentioned this Laurie et al. Paper before. So there is a kind of a fundamental problem in forced dissipative turbulence where this whole closure idea kind of works pretty well, and that's the question of predicting the profiles of these vortices, or often called vortex condensates, that emerge in forced dissipative two-dimensional turbulence. So the idea here is this is just like our problem, except there's no beta, and all of the energy, instead of going into jets in this problem, ends up going into vortices, which are called condensates by the physics people who work on this problem. And the idea is that you can do a kind of polar coordinate version of this same closure idea and then solve the resulting equation for the radial velocity profile of these vortices, and you find that they're that subject to the assumptions in the theory being valid in for a range of radius, the velocity profile, the theory suggests that the velocity should be constant, and that's indeed what is seen in simulations, as you can see in this picture up here. And there's a prediction for the constant of proportionality of root 3, which is realized pretty well. So this idea of there being a simple closure obviously kind of seems to do a reasonable job in this problem. And so there's a big question: why does it do so badly, or why is it give something nonsensical in the beta plane jets problem? And because obviously, as I said, there's no way with a closure like this you can end up with jets which on a scale which involves beta. Right. So what are the tools that we attack the problem with? Well, there are two kind of simplifications to the system which are kind of helpful for making mathematical and computational progress. And both of these approximations are thought, and I don't think that anyone has proved this formally, were thought to be kind of accurate in, or asymptotically accurate in the limit where z is much greater than 1, which is the giant planet's limit that we're interested in, where all of the energy in our system is going to end up in jets. And the idea is that you keep the same equation for the mean flow, the east-west flow, capital U, but in the equation for all of the wave-like disturbances, you either in this quasi-linear model, you neglect wave-wave interactions and just keep the linearized equation for the waves. So you have this model is called quasi-linear because the only nonlinearity is the momentum flux in the zonal flow equation. And then you can there's also a corresponding sort of statistical closure for this system, which is called CE2, and there are other names for this system actually, and it involves formulating an equation for the correlation, the sort of autocorrelation for the perturbation vorticity as a function of two different spatial coordinates, and you can end up with a PDE for this correlation function, which is defined on the domain squared, which is the reason for the subscripts 1s and 2s appearing here. This turns out to be an equation that you can make a little analytical progress with it, despite its forbidding appearance on this slide. And the point is, you can get the momentum flux, if you know z, you can get the momentum flux from this formula. So pi here is just this equation is forced by pi, which is just the correlation function for our stochastic forcing that we're putting into the model in the first place. Right. So I obviously need. I'm obviously going to have to do that every 5 minutes or so. Sorry. Right. Oh yeah. So well, so obviously the first thing that William did is to, or I made William do, is to check that we can implement these models numerically and solve them, and we get things that kind of correspond to each other. And I was saying the idea is that the quasi-linear and CE2 models both should be converging to the nonlinear model at large z. For practical reasons, our nonlinear simulations are at finite z, so there's a bit of disagreement between the nonlinear jets and the quasi-linear and CE2 jets. But CE2, if you like, is the statistics of the quasi-linear model, so there's good agreement in the equilibrium jets between these two systems. So these are numerical integrations of all three systems. So how does this help us? Well, Srinivasan-Young's theory for momentum fluxes all follows from the idea that you can find exact solutions to this z equation, CE2 equation, for the correlation function for the perturbation vorticity, you can find exact solutions in the special case where the flow is a linear shear. And why would we be interested in a linear shear? Well, if we're forcing waves at a scale which is much, much smaller than the jet scale, well, those waves that we introduce are only going to see the local flow, and the local flow will be linear. And so the idea is that the momentum flux associated with those waves ought to be a good, the solution to this equation ought to be a good candidate for a closure to the model. How do you solve this equation? Well, it's a first order PDE in Z. It's defined, the original equation for Z is defined on the domain squared, but because we're introducing a linear shear, it collapses into a PDE in 3 variables where X bar and Z bar are the differences in the longitudes and latitudes rather than the individual ones themselves. And so this is an equation which you might hope to solve, and Srinivasan and Young did solve it. They took Fourier transforms and solved the resulting equations using the method of characteristics. And they end up being able to write down an expression for the momentum flux in terms of the Fourier transform of Z in the form of this integral. So maybe the first contribution from our work, they give a kind of general expression for this in terms of the forcing pi that's very complicated and involves a sum over Chebyshev polynomials. William, I should give credit for a lot of credit for this formula, was able to produce this kind of simpler formula, which involves which has a coefficient outside it, which is the coefficient which appears in all of the simple theories, is epsilon over gamma, which is the ratio of the energy injection to the shear rate. And then there's a non-dimensional integral. This p epsilon that appears here is, if you like, is a distribution of which is like the density of energy injection at wave number angles in the initial forcing. So the idea is that this p is an object which integrates to 1, and it gives you it's like the density of energy injection at different wave number angles. So that where the wave number angle is the arctan of the vertical divided by the horizontal wave numbers. And then the other thing that appears in this integral is this which we call the kernel function k of theta, and it gives the contribution of each wave number angle to the momentum flux. And so the idea is that if you force at a different wave number angle, then each wave number angle has its own contribution to the resulting momentum flux. And the kernel function, there's a closed form expression for it. It's not very particularly intuitive because it involves the exponential integral evaluated at imaginary arguments, so not very easy to picture. But the advantage is that this is a nice closed form that can be evaluated cheaply in MATLAB, for example, where this function the exponential integral can be evaluated for complex argument. So what does the kernel function look like? Well, it has certain properties, and the properties allow us to understand the limiting cases highlighted by Fourier and Boucher and the previous authors, and also the Srinivasan-Young result that isotropic forcing gives zero momentum flux. So one property that this function has, so alpha here is this parameter which in the evaluation depends on friction and shear rate. So as alpha goes to 0, the kernel function goes to 1. And that means that provided, it goes to 1 everywhere except at plus or minus pi over 2, where it becomes singular. So the point is that, so provided you've got a cutoff in your wave number angle, this integral will, k will tend to 1, this thing integrates to 1, so you'll recover the Fourier-Boucher result And you can see why it happens by considering what the kernel function looks like. So we say in the limit of low friction, the kernel function looks like this red curve here. And this is it at higher values of the friction. But you can also, there's another result which you can prove, and that's that the kernel function always integrates to 0, and that's because this negative singularity here cancels out the positive value of 1 everywhere else in the domain, and that gives us the Srinivasan-Young result whenever the forcing is isotropic, because then this thing integrates to 0. So it turns out that both things can be true, and this framework is a relatively easy way to see that. In terms of a physical interpretation, well, the idea is that different waves introduced at different forcing angles contribute to the momentum flux differently. At low friction, so what you've got in this situation is these are pictures of wave fronts and how they evolve in time due to the shear flow. So if you start with a wave which is sloping against the shear, it gets advected over and eventually it has a tilt which follows the shear. And when friction is small, in the vast majority of cases, these waves get tilted over and they're not dissipated until they've got strong positive tilts. And in that case, the contribution to the momentum flux is always uniform and positive. But the exception is waves with an extreme backwards tilt, and they're the only ones that can contribute negative momentum fluxes at low friction. But one of the things that in practice means that the Srinivasan-Young result isn't observed is that if you've got a finite domain and you're forcing at finite wave numbers, you need to have access to a very, very long domain for any of these waves with extreme backwards tilts to be present. So in finite domains, you won't have these waves, and that's why in practical calculations, you always see positive momentum fluxes. So this mechanism is called the OR mechanism. It's been studied for over a century in Poisson flow, parallel flow, so this phenomenon of shears tilting waves, and it's been attracted a lot of interest in the 80s and 90s to do with non-normal growth, optimal growth, theories of optimal growth. Okay, so the next slide, if you like, is almost like the punchline of the talk, which is what some of these insights enabled William and I to do was to create a parameterization of stochastic forcing in the beta plane model. And so I'm just showing you that what we do, I'm showing you now what we attempted to do worked. And I'm going to try to make, for the rest of the talk, I'm going to kind of try to explain why what we did worked in some sense. And so the idea is that we took our original equation, this is the nonlinear stochastically forced equation, which gives us jets that look like this. And we replaced the stochastic forcing term with a deterministic forcing, which is based on the Srinivasan-Young closure, which is the local closure given by this formula, and this is just a zonal east-west force that we put into the model, and when we do that, we do see jets which look almost identical to the stochastically forced problem. But there is a kind of caveat that we need to mention. In our closure is not a purely zonal closure. What we had to do is put in some random noise into the wave components of our model and allow secondary instabilities to grow spontaneously. This forcing is a non-zonal, is a purely zonal addition to the equation, and it's completely replacing stochastic forcing. So there's nothing in the model to excite any non-zonal components apart from sort of spontaneously generated secondary instabilities. And when we allow those, they grow and saturate, and it's clear that they've got an important role in maintaining the jet structure. So again, this what we're plotting here is the absolute vorticity, or the potential vorticity, and showing the zonal flows. I hope you agree that what we're seeing in the parameterized and the full nonlinear model is pretty similar. It is just another plot of the same thing, except this time we're just showing the relative vorticity. And this is just another way of looking at what kind of waves have emerged in the parameterized flow, because here we're filtering out, if you like, the stochastic forcing that features in our original model. And you can see that there are waves on more than one scale, and particularly on the eastward jets, there are these relatively short waves, which are maybe waves 5 or 6 in the domain, and then on the westward jets there are somewhat longer waves. You can kind of see featured here, maybe wave number 1 or 2 on the westward jets. And so one of the things we're going to do is try to understand why these secondary instabilities emerge and why they look like this. So why did our parameterization work, or at least work as in the setup that we chose for it? We're going to sort of describe maybe 4 steps of analysis that we took. The first one is just to show that Srinivasan-Young works in the right setting, and that's how we're going to do that is we're going to do something called a scattering. We're going to do what we describe as a scattering experiment, where we fix the flow and don't allow it to evolve in time, and then implement the stochastic forcing part of the model, and demonstrate that the Srinivasan-Young theory predicts the momentum flux when this parameter f, which is the ratio of scales of our forcing to the scale of the flow, as that goes to 0. So that's step 1 is to show that Srinivasan-Young works in the right setting. Then we're going to do an experiment in a simple setting as possible, to show that if you don't allow secondary instabilities to develop, you get an answer that's dramatically different from what we're seeing in what the equilibrated jets look like. And then we're going to investigate the secondary instabilities further, first of all by showing that the equilibrated flow is close to marginal instability, and in fact it's close to marginal instability from more than one wave mode, one which lives essentially on the eastward jet and one which lives essentially on the westward jet, and that they both have a role in the momentum flux balance. And then we're looking at the momentum flux decomposition in our, and compare that in the CE2 and full nonlinear experiments. Okay, so step 1 is to do a scattering experiment, and the idea here is we just put in a sinusoidal flow, and we wanted to investigate whether the Srinivasan-Young momentum flux prediction, when the flow is fixed, works for different values of this parameter f, it's a proof of concept for convergence as f goes to 0. We choose a particular wave number forcing, which we're going to come back to for a lot of the calculations in this analysis, and that is, well, to point out that the theory is supposed to hold for any formulation of the stochastic forcing. We choose a particular stochastic forcing for reasons that become clear later, which is just fixed on a single zonal wave number, but has excitation at lots of different meridional wave numbers. And the reason for that is it makes this forcing makes it easier to diagnose which waves in the flows that we're looking at are directly due to the forcing, and which ones are due to the instability. And the reason is that's going to help us is that waves due to the instability are going to emerge at different zonal wave numbers to the forcing, and the forcing is going to contribute to waves at one particular zonal wave number. Okay, so what does this picture show? Well, these plots are the momentum flux normalized by the equilibrium energy, and the red curve is the Srinivasan-Young. The red curve with dots is the Srinivasan-Young prediction, and then the other curves are calculations from our CE2 model at different forcing wave numbers or different values of F. So we get down as low as F equals 7 times 10 to the minus 3. Sorry about that. What do we find? Well, we find that the theory does work at small f, as we hoped it would, and there's no reason why in this sort of static situation, there's no reason why it should not work. The issue is, how well does it do at jet cusps? Well, you have to actually go to quite low values of f for it to do well at the jet cusps, but eventually, and it does. As I said, finite f effects are stronger at the eastward jet than the westward jet. So the theory is pretty accurate for all 3 values of f at the westward jet, but it's less good at the eastward jet. Okay, so that's a scattering experiment, and it shows that if you've got a fixed flow, then the Srinivasan-Young theory does a good job of predicting the momentum fluxes due to these waves. How did we kind of establish that secondary instabilities play a fundamental role? Well, if we choose this particular forcing for our stochastic forcing, just with one value of the zonal wave number in the forcing function, if we switch off all the other wave numbers, there's nothing to excite them, and we can just let these are quasi-linear calculations in this case. We can just let these quasi-linear equations evolve spontaneously. We see that it evolves rapidly into alternating jets, which are very, very strongly unstable for reasons that we'll describe later. And these jets, the scale of these jets is limited by diffusion in the problem. Whereas, if in the quasi-linear calculation we introduce a very, very tiny infinitesimal seed forcing, so we excite other wave numbers, well, it's clear that other waves grow and reach a finite amplitude, contribute to the momentum flux, and give us jets that look plausible. And so this was our first kind of realization or hard evidence that the secondary instabilities are crucial to the equilibrium in these problems. If we want to understand secondary instability, we should do some linear stability analysis. If you've got a parallel flow in this setting, this has been studied back in the 40s by Kuo, and the original theory for parallel flows was started by Lord Rayleigh in the 19th century. But anyway, you end up with an eigenvalue problem for the phase speed of potentially unstable waves, which looks like this, and this is known as the Rayleigh-Kuo eigenvalue problem. If you put all the dissipation stuff to 0, you can prove a kind of necessary condition for instability called the Rayleigh-Kuo criterion in this setting, and that is that the absolute vorticity gradient, beta minus uyy, must change sign somewhere in the flow for instability. Otherwise, the imaginary part of this eigenvalue has to be 0. So what does our flow actually look like when you calculate this absolute vorticity gradient? Well, our flow, the velocity of our flow is this blue curve. So you can calculate the equilibrated flow is the blue curve. You can calculate the vorticity gradient, and you find that there are places where it touches 0, showing that there's some evidence of marginal stability because the flow is kind of close to the situation where the Rayleigh-Kuo criterion is satisfied, and these points occur at the flanks of the eastward jet and at the core of the westward jet. So what we're seeing here is that the instability problems associated with the eastward jet and the westward jet are kind of qualitatively different. So to investigate a bit more, we made it, or William, I should say, wrote an eigenvalue solver to solve the Rayleigh-Kuo problem numerically, and to get a little bit more insight into what's really happening, we introduced a flexibility by adding a kind of artificial parameter delta beta, which is kind of like perturbing the value of beta in the problem. And the reason we do this is if you reduce beta, you increase the tendency towards instability. So this allows us to see kind of the emergence of unstable modes, which are kind of near stability in the case where beta takes its actual value. And the result of that study looks like this. So this contour plot shows us the maximum growth rate of a wave. The contours, so red here is instability, blue is stability. And it's plotted as a function of the zonal wave number and this kind of artificial parameter which is perturbing beta. And 0, which is our actual flow, is here, which shows that in this particular example, we're just in the unstable regime for two different separate modes. And they're the only two modes that are unstable when we check the calculation. And so the features of these modes is that on the westward jets, the waves are longer, and that's just like we saw in our calculations. And on the eastward jets, the waves are shorter. So we've got wave number 6 on the eastward jets and 3.5 for the most unstable wave on the westward jet. You can calculate the eigenfunctions and calculate the momentum fluxes associated with these waves from those. And you see that those momentum fluxes act to blunt the jets in both cases. So what we can see is that the momentum fluxes associated with our original forcing are acting to sharpen the jets and make them and send them into an unstable state. These emergent instabilities will act to blunt them again, so we can hope for an equilibrium. So to kind of complete our analysis, we looked a bit at the momentum balance in the equilibrated states. These are calculations from the CE2 solution. And so the idea here is that we can decompose the momentum flux into a contribution from the which is direct from the forcing, which is given by the Srinivasan-Young theory, and we can demonstrate that for this equilibrium flow, that the momentum flux due to the waves at the forcing wave number is well described by the Srinivasan-Young theory. But then there's this secondary instability contribution from waves from these emergent instabilities. And in the jet cores, these are almost equal in opposites. You get huge cancellation between the momentum fluxes from the secondary instabilities and the momentum fluxes due to the forced waves in the core of the jets. And so, as I said, and this is our picture of the jet up here. This picture is the momentum fluxes associated with the different waves. I said the dark blue curve and the red is the contribution from the forcing, and the green curve is the contribution from the secondary instabilities. Here's another plot which kind of, I don't know if I'll talk too much about this. This compares quasi-linear and non-linear calculations and shows a kind of momentum flux, goes into detail of the momentum flux balance at different wave numbers at different parts of the jet. So this is showing the contribution from K wave number 4, which shows in this particular calculation wave number 4 is important at the westward jets, and then wave number 5 and 6 become important at the eastward jet. And then there's a comparable calculation for the full nonlinear flow, and there things are a bit more complicated because the flow is nonlinear. There's a lot of scattering of waves. There's also a lot of averaging because the jets are wiggling a lot more, and so you kind of get you see the same patterns in the full nonlinear calculation, but very much smeared out and smeared across a wider range of wave numbers. But the essential point that the secondary instabilities are playing a key role in the equilibration seems to hold. So anyway, I just return to the puzzles I set out at the beginning and sort of remind you what we kind of discovered. So can the Srinivasan-Young Boucher results both be correct? Yes, but the key thing is about the Srinivasan-Young result is that, which is that isotropic forcing gives zero momentum flux. Well, true isotropic forcing is unrealizable in any plausible domain. Numerical simulations of isotropic forcing give non-zero momentum fluxes. Well, the forcing is, that's because the forcing isn't truly isotropic. F is finite, it's important as well. What happens at the jet cusps? That's what we're interested in. So Srinivasan-Young does a good job, but secondary instabilities are absolutely key there. And how does the beta effect enter the problem? Through the secondary instabilities, both the eastwards and the westward jets. So this is like the final slide, I think. Can jet formation ever be described by a purely zonal closure theory? Well, no. What we not in this setup, not a typical setup, and that's because anti-frictional momentum fluxes push the system towards unstable states, and the waves that emerge are global, or at least at jet scale, and they appear on both eastward and westward jets. But as we've demonstrated, parameterization is possible in a non-zonal setting so long as you allow the secondary instabilities to develop. Whether that's actually very practically worthwhile, well, you can look at this. There is a saving here. Is if you've got a system which is forced at very small scales and you don't want to resolve the details of the forcing, well, you can plausibly use a parameterization. And that could be considerably cheaper because these emergent waves are on a larger scale, so you need a lower resolution. But unfortunately, it's not the case that you can just solve a zonal equation, which would be the ideal. Do I want to say anything else? No, I think I'm done. Thanks.
Thank you, Gavin. Very interesting. Questions? Engine?
Thank you for the interesting talk. First of all, I was wondering what the role of this, what do you call the view, and you call this friction coefficient? Why do you need it in the first place?
Well, because you need, if you want to equilibrate, you need you need to remove energy from the system.
I mean, you have the help of viscosity.
Yeah, but this is a two-dimensional turbulence setting, so the cascade of energy is to large scales. So if you want to have a physical energy balance, you have to remove energy at large scales.
So do you want to remove from the largest scale?
So if you relied on hyperdiffusion to remove the energy, you would get something horribly unphysical.
Yeah, so, and then and you mentioned the nonlinear simulation.
Yeah.
And so you solved that equation.
Yes.
And with using what value of n?
2. It's at the beginning. Yeah. Yeah. So n is 2, and the hyperdiffusion coefficient, hyperdiffusivity coefficient, selected in these types of problems to remove stuff at the small scales without polluting the rest of the solution too much. So it's a sort of art rather than a science.
Then results are similar if we were to use the normal viscosity n equal 1?
Yes, the role of the viscosity of hyperdiffusivity is just simply to remove stuff that's hitting the smallest scales. There are kind of some issues with backscatter, so there are small quantitative differences, but essentially the physics is identical.
Also, I didn't understand why you compare the zonal flow with zonal velocity with the potential vorticity. How are they the same?
No. So these are just showing two different things to get a. You mean why I showed this picture?
Yeah, I mean you need to compare the same physical quantity.
Oh, but this is the nonlinear picture. This is the potential vorticity, and this is the flow from the nonlinear simulation, and this is the same from the parameterized simulation.
Oh,
so I'm showing both.
Oh, okay. So
yeah, so the left hand one is the stochastic forcing one, and the right hand one is the deterministic one.
Okay, so what if you only want to plot the vorticity without the beta line? How would it?
That was this picture.
Okay, so you still have the band-like structure.
So yeah, so you got the banded structure is the same in the parameterized and the stochastically forced case. But there's more detail on the stochastically forced case because we've removed the small scale waves from this problem.
Yeah, thank you.
Yeah. Well, Guy and then Anna.
Have you seen significant differences in long to very long times between the nonlinear and the parameterized flow, especially in respect to the role of the secondary instability?
Well, these are equilibrated states. So we ran these models both out for a long time and then made statistics from the equilibrated states. So there's nothing changes, and they're in equilibrium. I mean statistical equilibrium. So is that answer the question? Sorry.
So it does not coarsen to the extent that you just have one jet.
No, because these problems all they saturate with jets at the Rhine scale. So if I had a bigger domain, a higher quantization number, we're going to get more jets. So there's no difference in the number of jets between the stochastically forced and deterministic ones. Although William did run out of PhD time, so we didn't explore it didn't do enormous numbers of calculations. But.
Yeah.
I'm not sure I understood correctly. When you say that you parameterize the instability, it's a different initial condition, or it's in addition to the parameterization?
So that is stochastic. So we're solving the same equation, but with a different initial condition, with the stochastic forcing replaced by a deterministic zonal force.
So you're saying that this equation has basically different attractors that it can go to, and it's always chaotic. Depending on the initial condition.
Yeah. Well, I mean, what we've demonstrated, I hope, is that the attractor is the same between the two models. That was the idea.
No, I'm saying the deterministic forcing, if I understood correctly, depending on the initial condition, you either go to this state or you, like you said, there is a big role to introducing wave numbers which are not.
Oh right. Oh yeah. So in the, yeah. So if you don't allow any secondary instability to develop, yes, you get a completely different attractor. Yeah, but that's a very artificial state because in any kind of turbulent situation, you're always forcing at every wave number.
Yeah, but I'm just asking about this deterministic model. The difference. I think I missed something. So I'm just asking if the kind of introducing the instabilities, it just depends on the initial conditions that you use for this model, or
yeah. I mean, you could do a version of this model where you artificially suppressed the instability, and then there'd be a different attractor, but that would be very artificial. So the idea is that we're allowing some kind of noise at other wave numbers, and then that grows into the instability.
And the other question is, so you're saying that the Srinivasan-Young formula works also at cusps, but then that's a bit confusing because it depends on the shear, right? It's kind of this local.
No. So the Srinivasan-Young theory is valid for any shear.
But kind of the intuition behind it is that it should be local, right? Like locally you can approximate the flow as a shear. So why should it?
Right. Yeah. So when there's no shear, the waves sit there and are damped, and they have whatever momentum flux it comes out of the formula. So the point is that this equation can also be solved when gamma is 0. There's nothing stopping you.
Okay, so you're saying it's just that you dump them. At the cusp, it's just damping.
Yeah, correct.
Well, in the actual system, I mean, of course, you do have some parabolic profiles.
That's right, but I think what comes out of this is if f is small, that the correction at high the correction at higher so actually was our first idea trying to solve this problem is, oh, well, let's do an asymptotic expansion in F and the higher order term will tell us everything. Well, that doesn't work, is our conclusion. So and the secondary instabilities. So and it wasn't until when we did this experiment we realized that it's not what's important, the higher corrections. The stuff in Srinivasan-Young about what the higher corrections look like, I think it's mentioned somewhere on one of the slides. Sorry, I can't find it. But yes, you can follow through the theory and do more stuff like that. So it was our original idea.
You can follow the theory through if you had.
Yeah, as an expansion in F.
Okay, but as an expansion in Y, I mean, because the point is that it's Y squared, right, rather than 0.
Yeah. So you still there would be some there would be some the curvature would become the important thing in the next order, I suppose.
Please.
So I think one of the puzzles you mentioned was that the parameterizations do not actually explicitly involve beta, and so it's unclear how they could capture the Rhine scale. And looking at the formulations for your parameterizations, it's not obvious seeing the dependence on beta.
Yeah, that's because the dependence on beta comes, and beta only enters the problem through the momentum fluxes of the secondary instabilities. So what happens is if you don't have secondary instabilities, the flow rapidly evolves towards a state which is unstable, and then it's that instability that allows things to equilibrate on the Rhine scale.
Yeah. So then, how does your parameterized simulations? Can you go back to the slide where you're comparing the full simulations versus?
Yep.
How do they capture the Rhine scale?
And because they allow the secondary instabilities, because we're allowing waves to grow spontaneously from other wave numbers, and then momentum fluxes from those waves create the balance for the jets on the Rhine scale.
Okay, so I mean, so we're going back to basically the classic, solution to this problem is that PV is being homogenized by instabilities, and that's
Sure, and that's a whole other perspective on the problem, which I used to work on myself in different aspects. Yeah, so PV homogenization is kind of it's kind of the mechanism by which the flow kind of reaches this marginally unstable state, if you like. So I agree. It's a different and complementary perspective. Richard is expert.
So another way of testing this in the full model. So if you took your DNS and zeroed out all the low kx modes and ran with very small scale forcing, would it evolve to an unstable state? Would you see?
Yeah, well, that's this
No,
flow.
that's the quasi-ring.
Oh,
If you took full
but
DNS
if you've the full model, yeah, I suppose. But I that would just be essentially equivalent calculation, wouldn't it? I don't think. Yeah.
Maybe.
Yeah.
I mean, a lot of work has emphasised the role of zonals, right? I mean, sort of long waves. You don't see a lot.
Well, yeah, but I mean, you could argue that. Hold on, are these not zonons? If you like these.
Well, so that they. Yeah,
I mean,
they're not wave 1 or 2. They're kind of they're shorter waves, which.
This is a wave 1 feature, isn't it?
Well, okay.
But I mean, doesn't that not depend on what? Surely the scale of the zonon is related to the jet spacing scale ultimately. So if you had a bigger domain, it wouldn't be wave 1 necessarily, would it?
I was just wondering whether in non-linear simulations you can actually feed energy up to kind of longest wave in the system. But you don't see the evidence of that.
And there's in our nonlinear simulations there's more scattering and more spectral power at a wider range of wave numbers as you'd expect. So there is some power there, but the momentum balance in this particular simulation is at slightly higher wave numbers.
I mean, coming back to the comment about so it's actually PV homogenization. Well, actually, but it doesn't look like that, does it? If you look at your velocity profile.
Yeah, I mean, so you expect to see PV modulation at very large, or more, something closer to PV modulation as Z increases, don't you? So yeah, so I suppose this theory is kind of like, it's a way of kind of explaining the deviations from.
It doesn't look very parabolic, does it? Between the jets.
Yeah, hold on. In fact, so there is a picture of the PV. Yeah, yeah, there's a non-zero gradient in most places, except for the jet flanks of the eastward jet and the core of the westward jet. And that's not.
So do you feel that this is PV modulization, or it would be?
No, well, I feel that there's an idealized limit in which you'd be closer to PV modulization. So, but it's obviously there's some finite frictions and things in this problem.
Can I just ask you about you had a comment at the end that says the forcing is not isotropic.
In our particular, in a lot of our proof of concept things, we choose this forcing because the theory should work for any forcing, and we put it all along one zonal wave number to make it easy to diagnose the secondary instabilities.
Talking about.
Oh yeah, right. Okay, so
yeah.
so then the point is that if you've got a finite domain and you're restricting the kind of forcing total wave number, then you can't have waves which are tilted too far back because kx can't be small enough, I think is the point. kx has got some minimum value associated with the size of your domain, and then if you're restricting the total wave number, you can't have waves which are tilted. So you can't have a genuine isotropic forcing in a you can't have an isotropic forcing that would work in the Srinivasan-Young sense in a finite domain.
I thought you could still come up with a numerical forcing that was independent of direction on average.
Isn't the issue that it's just this linear approximation, right? If that is some wave number, large enough wave number, you will see the fact that it's not a linear shear. So that's why this thing breaks.
But that's just another way it can break. I don't think that's what I was trying to get at is if you've got a finite domain and you take the friction to zero, at some point an isotropic forcing in the sense that would work for Srinivasan and Young is no longer possible. There are other ways in which it would also not work.
I mean, but you can have kx equals 0. You can reach the pi.
No, but kx equals 0 is not part of the wave forcing. That's the zonal mode. So you're trapped at kx equals 1 over the width of your.
You force it, right? You force. I mean, the other case are not 0, but you can force kx equals 0.
But the kx equals 0 forcing isn't it doesn't enter the wave equation. It's in the zonal equation. So it's not part of the. It's not part of the forcing that we're parameterizing. That wave doesn't get tilted because it's exactly 0.
Yeah,
Explain again why you are, I mean, linear stability analysis, what does it mean that you are using beta as...
So it was just a device to sort of show that they're unstable waves, that we're in a situation which is very close to marginal stability, because if you vary this beta parameter by a small amount, you become stable, and so you can see in reality in all of these calculations, the quasi-linear even in CE2 calculations are not. The equilibrated state is not steady, so we're really wiggling around this state, and also we were worried that averaging the mean flow kind of can be misleading in some other problems. So we just wanted to use it as a sort of way of sort of showing the structure of the instability kind of lying under the surface in the problem.
But so at the end of the day, then it means that I mean, when delta beta is 0, the jet is stable, the eddy is stable.
No, delta beta 0 is here, and so it picks up red for both the westward and the eastward jet with different wave numbers.
So just on delta beta.
The delta beta 0 is our kind of unperturbed problem. So anyway, the point is that this is a linear instability analysis of the mean flow. In the actual simulations, the flow isn't steady, so you can imagine that you're kind of fluctuating around this this structure in a multi-dimensional parameter space. I suppose that's the way I would look at it. I mean, the mean flow is just one representative. It's just a representative flow of where we're at. The flow is actually evolving in time. So that was the reason for just is to reveal structure. Is that the answer to the question? Okay.